Hi, I'm Todd. In this section, you'll learn some important properties about logarithms and how to approximate a logarithm to any base. Let's begin by reviewing the objectives. You'll learn some basic properties of logarithms and the change of base formula. So we'll start off by going through some properties of logarithms. For positive numbers, m, n, and a not equal to 1, and any real number r, the log base a of 1 equals 0. The log base a of m plus the log base a of n equals the log base a of m times n. The log base a of m minus the log base a of n equals the log base a of m divided by m. And the log base a of m to the r equals r times the log base a of m. Okay, so let's take a look at some examples. In this example, we're asked to use a calculator to evaluate each pair of expressions, then state which property of logarithms this calculation illustrates. So we have, in the first one, the natural log of 5 plus the natural log of 4, and we're going to compare that to the natural log of 20. In the second one, we have the log of 10 minus the log of 5. And remember, when we write log with no base, that actually is the common log or the base 10 log. So we're going to compare that to log 2. And finally, we'll compare the log of 5 squared to 2 times the log of 5. So let's start with the first one. We're going to compare the natural log of 5 plus the natural log of 4. So we'll take the natural log of 5 plus the natural log of 4, and that gives us about 2.9573227. And let's see what the natural log of 20 is. Looks like about the same thing. So the calculator is telling us that these two expressions are equivalent. Let's see what rule we might use to show this symbolically. Well, if we have the natural log of 5 plus the natural log of 4, that's equal to the natural log of 5 times 4, and the natural log of 5 times 4 is the natural log of 20. So we can also show that these two expressions are equal symbolically. Well, let's take a look at the second one. In the second one, we were asked to compare the log of 10 minus the log of 5, so I'll enter that. Whoops, don't need that many parentheses there. Log of 10 minus the log of 5. And that gives us about 0.301029997. And let's see what the log of 2 is. Looks like about the same thing. So again, it would appear that these two expressions are equal. Let's see if we can show this using the properties of logarithms. So we'll start off with the log of 10 minus the log of 5. Now, properties of logarithms tell us that we can rewrite this as the log of 10 divided by 5, which is the log of 2. So again, we can show symbolically that these two are equal as well. And finally, we'll take a look at the last one. In the last one, we were asked to compare the log of 5 squared. So there's the log of 5 squared. It's about 1.397940009 to 2 times the log of 5. And again, that looks like about the same thing. So again, the calculator is telling us that these two expressions are equal. Well, let's see if we can show symbolically that they're equal as well using the property of logarithms. We'll take the log of 5 squared. Now, one of our properties said we could bring this exponent out in front, which would give us 2 times the log of 5. So again, we can show symbolically that these two expressions are equal. Now, a lot of times we like to try to invent rules, and it seems like with logarithms that it's really popular to try to come up with your own rules. Here are a couple of errors that people use when dealing with logarithms. The log base a of m plus n is not equal to the log base a of m plus the log base a of n. Also, the log base a of m minus n is not equal to the log base a of m minus the log base a of n. Okay, so remember those two common mistakes. Let's take a look at another example. Here we're asked to use the properties of logarithms to expand each expression. And we have the log of x squared times y, the natural log of 2 divided by a, and the log base the log base 2 of the cube root of x squared divided by the square root of y. So let's see what we can do. We're going to expand each of these expressions, and we'll start with the first one, which was the log of x squared times y. Well, the first thing I'm going to do here is realize that I have the log of a product, and I can rewrite that as the sum of these two logarithms. So I can write that as log of x squared plus log y. And I can bring this exponent down in front, and we get 2 log x plus log y. So I've expanded that logarithm into the sum of these other two logarithms. Let's take a look at the second one. The second one, we had the natural log of 2 divided by a. Now, the natural log of 2 divided by a, we can rewrite as the natural log of 2 minus the natural log of a. And finally, in the third one, and the third one's kind of long, so I think I'll start with a fresh piece of paper. We have the log base 2 of the cube root of x squared divided by the square root of y. Now, this logarithm, the argument of this logarithm, involves some radicals. And often it's easier or it's convenient to convert these radicals to rational exponent notation. So I'll do that first. That'll give us the log base 2 of x to the 2/3 divided by y to the 1/2. Now what we notice is that we're taking the log base 2 of a quotient, and I can rewrite that as the difference of two log statements. So that would be the log base 2 of x to the 2/3 minus the log base 2 of y to the 1/2. And finally, I can bring each of these exponents out in front. And so that would give me 2/3 log base 2 of x minus 1/2 log base 2 of y. Okay, well, I'm going to give you a chance to try a problem now. In this problem, you're asked to expand each expression. The first one is log of 3 times x squared, and the second one is the natural log of 5 divided by z squared times y cubed. So stop the tape and give this a try. Okay, now I'll try the problem. The first one was log of 3 times x squared. So the first thing we can do here is write this as a sum. We have the log of 3 plus the log of x squared. And finally, we can bring this 2 out in front of this log, so we'd have the log of 3 plus 2 times the log of x. Let's take a look at the second one. In the second one, we had the natural log of 5 divided by z squared times y cubed. Now, in this case, we have the natural log of a quotient, so we know we're going to rewrite this as the difference of two logs. And that would give us the natural log of 5 minus the natural log of z squared times y cubed. Now at this step I have the natural log of a product here, and I can rewrite that as a sum. And this is an easy place to make a mistake. What you want to do here is you want to write this sum in parentheses so you don't forget to distribute that negative. So I would recommend writing it like this first. Natural log of 5 minus the natural log of z squared plus the natural log of y cubed. And by putting these parentheses in, you'll remind yourself that that negative has to be distributed through. We have the natural log of 5 minus the natural log of z squared minus the natural log of y cubed. And then finally, we can bring down these exponents. And that would give us the natural log of 5 minus 2 natural log z minus 3 natural log of y. Okay, well, hopefully we got the same answers on those problems. And take a look at another example. And in this example, we're going to write these expressions as one logarithm. The first one is the natural log of 3x plus the natural log of 3 divided by y. And the second one is the log base 2 of y squared minus the log base 2 of z. So we'll start off with this first one. And that was natural log 3x plus natural log 3 divided by y. Here we have a sum, so we can rewrite this as the log of a product. That will be the natural log of 3x times 3 divided by y. And 3 times 3 is 9, so we'll have 9x divided by y. Second one, we had the log base 2 of y squared minus the log base 2 of z. Now here we have a difference, so we're going to write this as the log of a quotient. And this is going to be the log base 2 of y squared divided by z. All right. Now, most scientific calculators have the common log and the natural log built in, or the base 10 and the base e logs. So what are we going to do if we have a logarithm that's to some base other than 10 or e? The answer is we need a formula, and the formula we're going to use is called the change of base formula. If we let x, a not equal to 1, and b not equal to 1 be positive real numbers, then the log base a of x is equal to the log base b of x divided by the log base b of a. Now, b can be any positive real number. And out of convenience, if we want to take a log of some base that's not 10 or e, then what we'll use for b is either the common log or the natural log. And it really won't matter which one we choose. Let me illustrate that idea with an example. Use the change of base formula to approximate log base 3 of 22 to the nearest thousandth. So the first thing we'll do is we'll rewrite this using the change of base formula. And remember, I can use either the common log or the base e log. So this will equal the log of 22 divided by the log of 3. And it also equals the natural log of 22 divided by the natural log of 3. So let's go to our calculators and see what that gives us. First we'll try the log of 22 divided by the log of 3. And that gives us about 2.813588, etc. Now we'll try this with the natural log. So we'd have the natural log of 22 divided by the natural log of 3. And notice that gives us the same answer. So in the change of base formula, we can use either the common log or the natural log. And we found that our answer there was about, I'll write the approximation down. It was about 2.813588, etc. That's, oh wait, actually we're supposed to approximate that to the nearest thousandth, so let me round that off. That's 2.814. So that would be our approximation to the nearest thousandth. Well, let's take a look at another example where we can solve an equation graphically using the change of base formula. Here we're asked to solve the equation graphically, express any solutions to the nearest thousandth. Now, in this case, we have the log base 2 of x squared plus 1 equals 5 minus the log base 3 of x to the fourth plus 1. Now, I can't graph either side of this equation as it stands because these bases aren't built into my calculator. But what I can do is convert each side to either the common logarithm or the natural logarithm using the change of base formula. So let's do that right now. The log base 2 of x squared plus 1, we could rewrite as the log of x squared plus 1 divided by the log of 2, and 5 minus the log base 3 of x to the fourth plus 1, we could rewrite as 5 minus the log of x to the fourth plus 1 divided by the log of 3. So what I'll do is enter each of these on my calculator as y1 and y2. So the first one is log x squared plus 1 divided by log 2. And the second one is 5 minus log x to the fourth, no, wait a minute, x to the fourth plus 1 divided by log 3. And in this case, the standard view screen should work fine, so I'll use Zoom Standard. And this is what the graph looks like. Now, the solutions to this equation are going to occur where these two graphs intersect. So what we can do is use the intersect feature on the calculator to find or to approximate those x values. So I'll press second trace, go down to intersect. Let's see, I'll choose this curve as my first curve. I'll choose that one as my second curve. And I'll move my cursor down towards where the solution is and press enter. And so this is telling me the intersection is at about x equal negative 2.034794. And that's an approximation of one of the solutions to the equation. You can see there's two because it intersects at two places. So I'll use the second trace intersect feature again to find the second intersection point. So let's see, I'll choose this as my first curve, and this is my second curve, and for a guess, I'll move it down close to where I think that solution is and press enter. And for the second solution, we get about 2.03479. And so we find that the solutions to this equation are x is approximately plus or minus 2.035, and that's to the nearest thousandth. Okay, in this section you've learned some important properties about logarithms, and you've learned how to use the change of base formula. These are very useful concepts, so be sure you do some examples out of your textbook so you solidify these ideas, and I'll see you next time.